This meeting is being recorded.
So you want to do this? Yeah, you want to unmute yourself, you can start, and it should be good.
I think we're actually unmuted.
Oh, yep.
Are we?
Do you want to do an introduction? I'll see if they can hear you.
Sure. Want me to proceed, Pedro? Or should I
We
do-
can proceed.
Okay, so I think we're all ready and we've got a few people joining us, and we're just going to do an audio check to make sure everyone can hear us. So we've got our audio technician, our audio engineer.
And if you want to pull up the chat, and great. In the chat, you can also ask questions, and I'll be monitoring that. We're good to go. They can hear us.
They can hear?
Great.
Okay.
Yeah, so welcome everyone. Good afternoon or good morning or evening, wherever you're tuning in from. So welcome to the UW, as we say, the UW, which is the University of Washington Geotechnical Engineering Program. And there are three of the faculty here to give an overview of the program and to talk to you. So I am Brett Maurer. I'm an assistant professor. And we also have Pedro Arduino to my left and Michael Gomez to my right. So the plan for this session is to give you a quick introduction to the program, our courses, what we're all about, tell you a little bit about what geotechnical engineering is all about as well. And we'll try to be pretty short and to the point, and then there'll be an opportunity to ask questions, and you can either actually type those questions in, I believe, and we'll be seeing those, or perhaps also they can speak through their microphones at some point. Okay. So without further ado, welcome to UW, and so what you're seeing here is essentially an aerial photo taken above campus, and we are here. So we're in Moore Hall, and it's really a beautiful campus. So what you can't see in the photo is that we're just about a 2 or 3 minute walk from the Seattle light rail system. So if you walk just 2 minutes, you can then get on the train, and in 5 minutes, you're downtown, and beyond that, you're maybe at Mount Rainier or wherever you'd like to be. So it's really an exciting and a pretty beautiful place for all of us to work. So just a little bit more about life at UW. There's the train that I mentioned. So you go to Husky Station, and in 6 minutes you're downtown. You can be at Pike's Place Market. You can walk the waterfront. You can get on a ferry. And as a student, all of the transportation is free to you. So you can ride the train, the bus, the ferry, all for free. And so that means going places like West Seattle or Alki Beach. So even though we're in the Pacific Northwest, we actually have some really nice sandy beaches where you can play volleyball. You can head to Mount Rainier National Park. Of course, there are whales here. So I think the thing that we probably all really like about Seattle is that whatever you're into, whether you're more of a city person or whether you're more of an outdoorsy person, whatever your interests are, you can find them here in pretty close proximity. So I think I'll let Pedro Arduino maybe chime in and just talk a little bit about how our department is structured at this point.
So in civil engineering, civil and environmental engineering, we have 6 areas: structural, geotech, transportation, construction, environmental, and water resources. And we are one of them. So geotech is one of them. We have 5 faculty that are full-time in this area. Myself, and then Michael Gomez, that is to my right, Brett Maurer, that is in the middle, and then Steve Kramer and Joe Warman. And then there is also an emeritus professor that is called Bob Holst that stops by from time to time. So it's 5 people that is working in this area at UDAP. We also have some additional instructors. We have the benefit to be in an urban area that does a lot of research, a lot of work, a lot of technical work in geotechnical engineering. So they stop by from time to time to give seminars, or they run classes like a case histories class in geotechnical engineering. And of course, they also give seminars. They are guest speakers for seminars throughout the years. We also have an ASC chapter. We have a graduate student group that organize seminars and visits to geotechnical firms, etc. So just to mention that it's not just the 5 of us, we also have the benefit to bring the practice around us to UDAP. So just a little bit of what do we do? Why do we have a field in geotechnical engineering? So the first thing is to understand what type of material we are dealing with. And the material that we deal with is rock and soils. And these are materials we build on or we build with. So here you're seeing a picture of a dam. This is an engineered dam that is made of soil. And that soil has to be engineered. Here you have a top view of the same dam. So you cannot dam the soil there without looking at the properties, checking the engineering properties the same way that you do with concrete design or steel design or wood design. This is just another material that you have to work with. So we measured a lot of the properties, and actually some of Mike Gomez and Brent Norton, they have a lot of experience getting the strength of the material, the elastic properties, the permeability, the compressibility. So we have a lot of equipment that is used for this purpose. A lot of that is very advanced, and we have them available here at UDAP. Also, you do field tests. Sometimes you cannot bring samples to the lab. So what you do is to go to the field and you perform tests in the field. And there is a whole variety of tests in the field that they run in between what is called SPT, dilatometer, comb penetration test, pressure meter test, vein shear test. A lot of tests that you perform in the field in order to estimate the properties directly there on site. And we have a lot of experience on that too. In particular, Professor Bob Halls was an expert on some of these methods. We evaluate the stability of slopes. It's very common to have the need to build a slope or to put a structure on top of a slope, either because visually it's better, you get a better view of the sound, or sometimes because you are making a cut and you have to build near some of these very high slopes. So how to evaluate the stability of these? You may have problems. That sometimes they are small, but sometimes they are very large, like in the case of the Oslo landslide a couple of years ago that resulted in the loss of lives, of many lives, and in addition to all the economical losses. So how to evaluate these so that we don't have this type of problems is something that we do in our field. What else? We also evaluate hazards, in particular in this area, earthquake hazards. And you know, you have, or we live on top of a very thin layer of soil, and underneath that layer there is a rock. So waves that come from an earthquake, they propagate through that soil, and usually that little mantle or little layer of soil acts like a huge amplifier or de-amplifier or modifier of the motion. So it's very important to understand what is the soil going to do to the waves that are traveling there. And that's something that we do. So site response depends on the type of soil, the thickness of the soil, the stiffness of the soil. And these are all things that we do. If we don't take care of this, we can have problems like this one, where this seems to be a structural problem, but if you look more in detail at these buildings that are tilted, you will notice that structurally they are in great shape. The problem is that the soil failed beneath them. And because of that, they had to be completely demolished. And fortunately, in this case, there were not many lives lost. This was in Japan, in Niigata, many years ago in the 64. What we do, a lot of the things that we do is to conduct reconnaissance activities to learn from recent disasters. And we have had several of those in the last couple of months, actually. So we have people that go to these places, they collect information, and we try to learn from these problems so that these things don't happen again. On the left here, you have a picture of Professor Joe Warman. On the right is a picture of, actually it's me, in Mexico City. This is a picture of Professor Kramer on a landslide here in Olympia after the 2001 Nisqually earthquake. So we do go to these places, we learn from them, and we try to prevent this in the future. This here says Taiwan, but it's not Taiwan. This is here. I took that picture. So what else do we do? We build, design, and construct tunnels. Actually, here this is a submerged tunnel. It's a drawing of a submerged tunnel that is crossing a lake, maybe Lake Washington. And actually, this was a project that we did many years ago when we were still thinking about the new 520 bridge or maybe a floating tunnel. Well, we ended up with a floating bridge. But the important thing here is that either the floating bridge or the tunnel has to be restrained at the bottom with some anchors. And that's a geotechnical problem. And that's the difficult part, to make sure that these constraints, these restraints are in good shape for the next 20 or 30 years. Tunnels are usually in soils, and actually, I don't know if you know, but one of the first tunnels in soils was built here in Seattle, actually crossing for the I-90 highway when it was getting to Seattle. Since then, we have done a ton of these tunnels in soils. That's the difficult part. How to do that without the soil collapsing on you? And if you go from the 1960s to today, this is a picture of the SR-99. This is Bertha, the TBN machine that was used in order to build the tunnel that's going to be open next year, I think in February. Again, the largest tunnel in soil in the world for the time. It was in 1960, it's again here in 2018. So we do the design of that. We evaluate groundwater flow, how the water flows through soils. And that seems to be kind of like in this picture, like an agricultural problem. And you look at how the water soil, well, but in reality, if you don't take care of how the water flows through the soil, then you may have problems like the breaching of the levees in New Orleans a couple of years ago that resulted in the loss of many lives and economic losses, as you may know. Is this a geotechnical problem? It's an interdisciplinary problem between the hydraulics people, the geotechnical people, and the structural people, and social problems, because why do we put these things there? Do we need to put a city in a place that is underneath the water? So it's a very interdisciplinary problem where we all play an important role, including geotechnical engineering. We also improve the soils. So these moon people, they are not in the moon, they are actually here, but they are trying to use some chemicals in order to improve the characteristics of this. What characteristics? Well, the strength, the permeability. If we want to prevent the water flowing through the soil, well, we have to change the permeability. If the soil here has a strength that is bad, or a strength that is affected by liquefaction, well, let's mitigate this problem. How? Improving the soil. And actually, I have next to me is Michael Gomez. He's an expert on that. And that's why we are very happy to have him here in the group. This is those soil mixing. No? Soil mixing, so you mix concrete with the soil clippings and you end up with a slurry that is much more strong than just having the soil there. And this one, what would you want to say with this one?
The idea is just that, so kind of increasingly we're looking at the impacts of different soil type of techniques. And recently we've come to realize that we can use chemical and biological reactions in the soil. And sort of kind of the new generation of looking at ground improvement is trying to look at things like how can we use microorganisms or chemical reactions to help us do that. And one of the things we're looking at is actually using bacteria to do some of this soil improvement for us. So it's kind of an interdisciplinary linkage between geotechnical engineering, between microbiology, and also kind of looking now more towards biogeochemistry and these sorts of things. So it's an exciting time.
Yeah, again, we have to get out of these silos that are just soil mechanics. It becomes interdisciplinary. So we need to do chemistry for doing this type of problems. We need to do biology here. We need to understand how these bugs grow and move around, how to control them, how to tell them, go here or there, poop here or poop there, because that's what they really do. and that's really an interdisciplinary problem. So again, more on the tunneling. Lately, we have seen several activities related to tunnels. One of those was next here to the light rail, with the tunnels that go to downtown Seattle. In next year, we are going to open another part of the tunnel that goes all the way to the north. We are crossing also to the east side. So we are going to see tunneling much more in the next couple of years. And the technology that we use for tunneling is complex. It involves understanding a lot how the soil that you are cutting behaves, in addition to understand everything else. It's a structural problem too, and it's a construction management problem too. And this is a picture from a couple of years ago for the tunnel in the light rail station here at UW, next to the Husky Stadium. And that's how the construction site used to look like. Now everything is covered, you don't see anything, but below there is a big hole that needed to be done in order to build this. This is another picture of the same construction site for the UW station. Here you see the walls on that excavation. These walls had to be heavily reinforced so that the soil doesn't collapse on top of you. And believe me, the loads that come from the soil are huge, are tremendous. So these are very strong walls. And this is the inside of the tunnel when they were building this with a tunnel boring machine, or TBM as it is known. We also do a lot of simulations because sometimes we have structures like this bridge, and then we say, well, what would happen if this bridge is subject to an earthquake? We don't know if the earthquake will happen there. So we have to start doing modeling. We do finite element models. And these finite element models are three-dimensional. They include not just the soil, but you have to start modeling the abutments, the embankments, the piles, the interaction between the piles and the soil. So the numerical component of this becomes very heavy. And again, very interdisciplinary between geotech and the structural people and the mechanics people, and of course, all the numerical people. This is another case of a bridge in Chile that collapsed. And again, we did the whole analysis of this bridge, including the foundation, the piles, and so that we can understand better what happens. So what I'm trying to say is numerical modeling is a very important component of what we do. It can become difficult, for example, when you are doing the analysis, very simple analysis of a bucket of soil that you are trying to turn, how to model that the soil is moving like that. This is not a simple analysis, it's numerical analysis, how to do that in the proper way so that you get realistic and accurate numbers. Also, we model water. If we can model the flow of that granular material, what happens if you try to model the water? This is the case of a tsunami that is impacting a bridge. The bridge is represented by the little structure. So when the tsunami comes, of course, it crashes into the structure. So we want to know how much are the loads. so that we can design better the bridge structure. So with that, I think that I have given you an overview of what do we do. Particularly, I have tried to emphasize all the areas that we do here at the University of Washington, where we have faculty with expertise with that. So with that, I think that now we should move more into the program, our program itself. And I think I will leave that to Brett, so maybe you can go into that.
Sure. So that's that's a very good overview of what geotechnical engineers do. So how about in Seattle? And one of the really great things about being here is that it's really a booming city. And everywhere you look around, there's some kind of construction, there's some kind of mega engineering project. And so as students, when you're here, you're very much exposed and in contact with all that's going around in Seattle. So maybe you've seen this particular figure or this stat before, that in fact Seattle has more tall tower cranes than any US city. And so case in point, the next photo you see, I'm not sure that it's all of the cranes, but it might be about a third of them. There's about 21 shown here. And again, you see sort of the boom town that Seattle has become. So there's all kinds of really interesting geotech projects going on. We have what is called the I-99 tunnel that is just about to open, and this is going to carry cars. But we also have the light rail tunnel, and so the light rail currently serves the university, and in about a year or two, it's going to open north of the university. And so a lot of students who might currently walk to school or take the bus, now they'll just hop on the train, and they'll arrive almost exactly underneath Moore Hall, where we work. There's of course lots of really deep excavations, all kinds of activity going on with Amazon. So you might be familiar with what's called the Amazon bubble in the lower left. And in the lower right is the famous Oso landslide that killed many people. And you may have heard of Oso, but you might not know that it's located just outside of Seattle. So the point being that when you're here, you're really very much involved with this network of alumni. We have a very active geotechnical scene. Every month we have seminars, guest speakers. There's always some opportunity to interact with practitioners and with alumni. So I think it's a big part of what makes our program really special. So a few details, what does it look like to actually get a master's degree or maybe a PhD? So with the master's degree, you can take two different paths. So it's exactly the same degree, it has the same title, but the first option is to do what's called a research master's program. And with that, well, it's what it sounds like. You do research and it results in a thesis. The other option that's quite popular is called the professional master's program. And with that option, you are strictly doing coursework. It doesn't mean you can't do research. You, for example, could do an independent study for credits. It's just that the research will make up a smaller portion of your overall credits. And then, of course, you could go on to do a PhD. So a few more details are shown here. So the two master's options, either option, you need 42 credits total to graduate. With the research option, you would typically do 9 credits of research. So you write a thesis and that would count for 9 credits, and the other 33 would come from coursework. With the professional track, again, 42 credits, but it's all coursework. So obviously that's a few more classes, probably 3 more classes. If you're interested in doing a PhD, that is a total of 90 credits. And importantly, you get to count 30 of your master's degree credits. So it's not as many credits as it might sound, because once you've done a master's degree, in fact, it means only taking another 1 year of coursework. And the rest of the PhD, it's of course all about research. And So there's a few exams that go along with that. This is pretty typical, whichever program you might go to. So you have the qualifying, the general, and the final exam. It sounds kind of scary, but it's really not. Only the first exam really resembles what you think of as being an exam. The other two are really just presentations, and I think of them as more so being a celebration of your work and of what you've accomplished. They're not something to be stressed about. So this is a listing of all the geotechnical classes that we offer. I think it's really quite an extensive list compared to many programs in the US and around the world. So we have a total of 11 courses that are strictly geotechnical, and they're taught by one of the 5 geotechnical faculty. And if you're keeping track, you need 42 credits. And so as is shown on the right, that means that you need to take probably 1 or 2 elective credits. And those can be really in anything that you're interested in. They're almost completely free and open to your interests. So many students go into earth science or applied mathematics, or they go to the law school, they go to construction, and so on. So here are the geotech classes divided into our 3 quarters. So you may actually not know that we're on the quarter system. And so we have 3 periods of school rather than the 2 semesters that some may be used to. And so the quarters are 10 weeks long. And if we look at our curriculum, it is sort of roughly organized into classes that are more fundamental, and you then gradually transition into classes that are much more applied. And so your first quarter, you're learning basic soil mechanics and soil chemistry, and you're in the lab. And by the time you graduate, you're learning how to apply all of that fundamental knowledge to earthquake engineering problems, to foundations, to retaining walls, to slope failures, to all of the things that practicing engineers do. So one really interesting and I think unique thing about our program is that you can actually do it in just 9 months. And I don't think too many programs have that situation. So, I don't have exact numbers, but I would guess that about 2/3 of our graduate students choose to do the program in 9 months. So it is intense, but it's very doable. And in some sense, it's a very efficient way to get a master's degree because you get in, you work hard, you learn a lot, you have fun, and then you go on to your professional career. The other probably 1/3 of the students are either on a track to do it in, say, 1 year. They take a little bit more time by choice, or maybe they're really interested in getting a taste of research. They're thinking about whether they want to do a PhD, and so that experience is important. Or sometimes students do master's degrees over very long time periods. So they are working full-time and they take 1 or maybe 2 classes each quarter. And that's possible to do, and we always have people in the program that are doing that. So I mentioned already that with those elective credits, you can go out and do just about anything that you want, and we very much encourage that. So a little bit about our program, who are the students? Well, we typically have about 20 to 25 students, so you might think of us as a medium-sized geotech program. And I think one of the really great things, especially at the moment, is we have a really diverse group. So we have about 50% women and 50% men, and we have students from a number of different countries. So I think it's a really great thing about our program. We have a student group called GIGS, which is the ASCE Geotech student group. And so they are always having activities, field trips, social activities. They have a Geo Beers meeting. So once a week, the students get together and have a little fun together and catch up. So a little bit about admissions and financial aid. I know that's always of interest to everyone. So first of all, the applications, they're reviewed by the 5 geotech faculty. So we get together and we talk about all of the applications. And when it comes to financial aid, there's a few forms that can come in. So either it could be a teaching assistant position, and I think everyone knows what kinds of things TAs do. So there's a few of those positions, and of course they're competitive, just like any other funding option. We also have fellowships. So many of the geotechnical engineering companies in Seattle, they donate money that then fund students. Of course, they're really interested in hiring and recruiting students, and so they see it as a great investment to fund a part or maybe even all of your master's degree. And then, of course, there are research positions. So that depends a lot on the availability. It's very much kind of a matter of timing. It depends.
This meeting is being recorded.
Sorry about that. So I was just muted, not knowing it, but I think we lost our connection briefly. So sorry about that, but I think everyone is still here, and we'll pick back up where we left off in just a second. Okay, so I think we're. Am I displaying my screen?
No, you need to share your screen again, but your audio is good.
Great. Okay, so share screen. Okay. No, we're still not displaying the screen.
You got to say share screen. There.
Great.
Great. Sorry about that again. Okay, so that's the details on financial aid. And I think just before it cut out, Pedro was saying that probably the majority of students in the program do receive some kind of funding. So it doesn't mean that they're fully funded, but the point is there's actually a really good chance of getting financial aid. So just a few more slides we have about the student activities. So one example is the Pacific Northwest Graduate Student Symposium. So this is a geotech specific conference that is just for graduate students from all of the universities in the Pacific Northwest. And I think, in fact, we're actually planning to host this next year. So it's something that you might get to be a part of. We have all kinds of outreach activities, and outreach means interacting, for example, with younger students. Engineering Discovery Days is a special event that we have every year, and it attracts about 10,000 students from elementary school up through high school. And as graduate students, you, for example, might be teaching them about geotechnical engineering. So some of our students demonstrate tsunami hazards, some demonstrate liquefaction, and this is all about hands-on activities and kind of motivating and encouraging the next generation of engineers. So we have social get-togethers. This is a photo from our most recent Geotech potluck that was actually at Professor Arduino's house. And this is probably most of the students, but not all of the students. So just a few things about our lab capabilities, which have really improved, or let's say grown tremendously in just the last couple of years. And I think I'll let Michael Gomez tell you just a little bit about the lab, because he's been a big reason for all of the new infrastructure that we've gotten lately.
Sure. Yeah, so we have a lot of exciting new type of equipment in terms of the laboratory for the geotechnical graduate group. This is just kind of showing a picture of the graduate lab there, where there's a variety of different equipment looking at kind of basic soil classification. So there's sieve analysis, there's hydrometers, this sort of thing, going through Atterberg limits, as well as being able to test permeability, looking at consolidation behavior with odometers. We were fortunate to get a new direct simple shear piece of equipment, which can do both direct shear and simple shear type of tests. And we're hoping to always expand our lab capabilities and hopefully get some new interesting stuff like bender elements and be able to do geophysical tests in the lab as well. So we're excited and thankful to have a lot of new equipment and kind of new capabilities to look at soil behavior and also do some more kind of interesting things in the lab class, as well as kind of link it in with some of the other courses that we have as well. This is kind of looking at some of the more specialized type of equipment. Here up on the top right, that's Professor Arduino's True Triax type of device, where you can look at stress states that you really can't do in a traditional type of triaxial piece of equipment. There's also a resonant column device, which can look at basically changes in shear stiffness at different amplitudes, and so it can be important for looking at type of site response or earthquake engineering type of applications. There's a variety of equipment from Professor Holtz that was looking at geosynthetics, and a couple of exciting and kind of unique pieces of equipment like this K-Knot odometer type of ring, where you can look at interesting problems that are geoenvironmental or maybe geotechnical in origin as well. Let's see, whoops, I might have passed that one up. This is just kind of looking at some of the newer facilities downstairs, which we have for geotechnical research. And so we have some new equipment from GDS, which has basically a new triaxial device, new abilities to do consolidation tests and unconfined compression and this sort of thing, as well as a dynamic direct simple shear, which can actually start to look at loadings that would be potentially important for earthquake engineering applications. So we're looking specifically right now at characterizing kind of biocemented materials, but certainly these things are available for graduate research and for your learning, essentially to learn about how to do geotechnical lab characterization and to learn about the response of these different types of materials when subjected to loadings characteristics of different applications. And so that's available there as well. This is just a slide here, kind of plugging the new Rapid NERI facility, which is headed by Professor Wortman. This is looking at actually doing natural hazards reconnaissance. And so there's a variety of different equipment, be it drones or LiDAR, there's even dynamic cone and this sort of thing. But the idea is to be able to go to locations that have had natural disasters and be able to collect more perishable data in order to understand why things happen and potentially to improve design in the future. And so this is a really exciting facility that's in the natural hazards community, and it actually serves the entire United States. And is part of kind of a bigger network of different things, looking at maybe centrifuges or geophysical testing and this sort of thing. And so researchers from around the country can work with Professor Wortman and his team there at the Rapid facility and deploying these different things and going to places like Indonesia, Japan, where they've had recent disasters, being able to collect that data and then try to make sense of it and improve how we do geotechnical engineering specifically for different hazards. And so This is just kind of our overview of the geotechnical faculty. We've got 3 of us here over on the far left of the screen as well. There's also Professor Wortman, Professor Kramer, and Professor Holtz. And I think now this is going to kind of lead us into talking about some of our individual research kind of interests. And so this is
and we are going to go very quickly on this. Just to mention, what do we do? This is me a little bit younger. A couple of years I had dark hair once, but I have hair. You will see it. And I do a lot of what is called computational geomechanics. So I'm really interested in the numerical methods applied to geotechnical problems. I do constitutive modeling, mechanics of porous media, soil foundation interaction, large deformation problems due to, for example, big landslides or even tsunamis. So it's all related to the computational geomechanics aspects of the field.
This is me, and so my research interests are primarily around what's called biogeotechnics. It's this idea of being able to use biomediated processes in the ground, either by bacteria or algae or something else, as well as the idea of looking to nature for inspiration. So that's kind of the idea of bio-inspired designs, where we might be looking at designing tunnel borings like ants do, or perhaps designing piles in a way that's similar to how trees might stabilize themselves. And so this is kind of a new field that's being formed. There's an engineering research center associated that we're linked up with too. And it's kind of looking at how can we use these things that nature has already done for perhaps hundreds of years or thousands of years, and try to apply them to geotechnical problems. I'm specifically looking at biosegmentation for ground improvement. I'm interested in a lot of different advanced soil characterizations. And a lot of my research has to do with looking at these biogeotechnical solutions, and specifically biomediated solutions, and applying them to things like looking at how does the biosegmentation degrade, what is the response of these different types of materials, and how can we develop or come up with new ways of using these mechanisms for our engineering purposes.
So this is Professor Bob Holtz, and he's a retired, so he's an emeritus faculty, but he had a big impact on the soil improvement field, including geosynthetics. He's one of the creators of the geosynthetics field. He did a ton of in situ testing, also characterization of soil properties in the lab, and a lot of work in foundations. So we are lucky that he's around us from time to time. So very well-known guy, because he also wrote one of the leading books in geotechnical engineering that has been used for decades. So this is Professor Kramer, and he's an expert in geotechnical earthquake engineering, and he's the author of one of the leading books in this field. He's also very well known for his work in liquefaction triggering and liquefaction effects, and also for the work that he's been doing on the ground motion field. Very well known faculty and engineer, and we are also lucky to have him in our club.
Yeah, so this is me, and a big part of what I do is also focused on geotechnical earthquake engineering. So for example, soil liquefaction, I work on models to better predict liquefaction, to better predict the consequences for structures, and then to use those models to make better decisions about when, for example, to mitigate liquefaction. I also study something called paleoseismology, and the basic idea there is there are a number of places in the US and around the world where we know we have a big earthquake hazard, but we don't really know much about the earthquakes. So we maybe know that there was a big earthquake. So for example, in Missouri, excuse me, in 1811 and 1812, we had what may have been the biggest earthquake in recent history in the United States. But other than the fact that we know there was an earthquake, we don't know very much about it. The only thing we do know is that it left behind soil liquefaction. So we can perform a forensic analysis on that evidence, and we can work backwards to try to better understand characteristics of the earthquake. So I'm interested in doing those studies in the Pacific Northwest, in the central US, in Missouri, and in a number of other seismic zones as well. And then lastly, we have Joe Wortman. So we already said a little bit about Dr. Wortman because he is the director of what's called the RAPID facility. So he's very much interested in post-earthquake reconnaissance and technologies. And other than that, one of his primary research interests is in landslide hazards and slope stability. That may mean developing new landslide models. It also means going out and studying landslides when they've happened using drones and other types of technologies. So I think that brings us to the end of our slides. And so we'll leave you with another beautiful photo of Seattle. Again, I think what we all like about Seattle is that whatever our interests are, I think we find them pretty close, whether it's interest in the city or interest in the mountains. So I think you have the ability, if you're so motivated, to type in questions. And
yeah, so yeah, please open the chat and type any questions.
So if you have questions, we'll see those and we'd be happy to answer them. If there aren't any questions, we appreciate you joining us, and we have one.
Yeah. So first question is, I understand there are several positions open, such as TAs. Does UW have lab assistants or similar positions?
Yeah, so a lab assistant, I suppose, could mean a couple things. It might mean a research assistant in the lab, and yeah, in fact, we always have a number of funded grad students doing work in the lab. It might also mean that you're a TA and you're in the lab teaching the undergraduate lab course, and we always have grad students doing that as well. So absolutely, every year there are opportunities to be a funded lab assistant.
So yeah, we are lucky that in our soil mechanics class includes a lab component. And our graduate lab also is, of course, a very intense lab activity. And then, so those will require TAs. And the TAs are usually either the new master students that apply. We try to use that as a recruitment for somebody that wants to come to the University of Washington and is good in the lab, so we can use that. But also we do research in the lab. And in particular, now that we have Mike Thomas, you have had graduate students and undergraduate students, both of them.
Yes.
So these things happen.
Do you know how many research master students you typically accept each year? And do you know like what percentage of the professional masters versus the research option?
Mm-hmm. And Eric, is everyone able to see the questions that come in, or shall we repeat them?
They should be able to, but you can feel free to repeat them or summarize them.
Yeah, so the gist was, how many research master students are there? What percentage of master students do research? I think that was the question.
Yeah.
Right? Do you want to answer that, Pedro?
Yeah, I don't know if the question is that, or how many of those are in the professional masters or in the research masters. I would not look at as a big deal. We have a lot of students that want to do research, but they start in the professional masters. They start in the professional masters, they take classes, and then they say, oh, I want to do research. We have some other students that want to start in the research component, and then they move and say, oh, I just want to do the professional one. And they move to the professional. So you always have the option to do one or the other. If you are receiving some funding from a grant that is for a research activity, we expect that that student is going to be doing a thesis, hopefully. Sometimes when you get a large fellowship, like the Balde Fellowship, we would expect that you also write a thesis. So we would like to see that student in the research component. If you ask me right now, in our current group, how many are in the professional or in the research, I would say that at least 2/3 are in the professional one, and 1/3 is in the research one.
Mm-hmm. And I'll just add that on your application, you're asked to pick which of these two master's programs you're interested in. And I would encourage you just to go with your gut feel with what you think you want to do, but you shouldn't worry too much about what you've put there. It does not really have a big impact on how we view your application or how we decide on your funding or your admittance, for example.
Along those lines, a question that's come up a lot is, should you be reaching out to faculty if they're interested in research and trying to connect before admissions? What's your group's feel on that?
Yeah, so we may all have different opinions about that. So as for reaching out and saying that you're interested in research, I think it can always be a good thing to do. But you should also understand that the positions are always a matter of timing, that faculty at any university, they don't usually know how many students they'll be able to hire. So faculty may be very interested in you as research students, but they may or may not have funding, or they may not know if they will at that moment. So it doesn't hurt to reach out to faculty and say that you're interested in research, but you shouldn't be too disappointed if you tend to get responses saying, well, I just don't know right now, and I encourage you to apply.
Yeah, and in some cases, when somebody has chosen the professional one, and we may say, oh, but look, he or she talks about doing this or experiencing that or that. So we can even send you an email. Hey, are you interested in doing this research? And do you allow us to change you to the professional one? And maybe you get an RA, research assistant. So that's also happens. Don't worry too much about that. That's different in many other groups. So it's not consistent in all the groups in civil engineering. Some other groups, they really differentiate between the professional and the research students. For us, and that's also in the structures group is the same, you are all in the same group. And
I would also add to that, if you're in the professional master's program, it doesn't mean that you can't do research. So there's always the option to do an independent study. If there's a small research project or thing that you can do with one of us, and perhaps you're interested and just want to try research out and see what it's like, there's always an opportunity potentially to find a kind of an independent study type of scope of work and be able to do that too. So that's always an option.
Mm-hmm. And you can also switch which of the programs that you're in once you're here.
There's a question here about if any of the faculty do research related to buried pipeline geohazards. Do you know if anybody does that in the group?
Yeah, so the question is about pipeline hazards. And I think probably a number of us indirectly study pipeline hazards because, for example, we study soil liquefaction and the effects of liquefaction on infrastructure at the near surface. In terms of, say, doing full-scale pipe testing, there's no one here that's currently doing that kind of work, but we very much do indirectly study pipeline hazards.
And we have done a lot of reconnaissance work, because every time that you have an earthquake and maybe there is liquefaction or maybe subsidence like displacements, pipelines, it could be water or sewer, they are affected. So we have done a ton of work on reconnaissance and evaluating the damage and connecting with what's the process after the damage has happened, how to recover from that. So yes, we do some work on that.
So I think that's all the questions we have. Feel free to chat me another one or two if you have them. Otherwise, for logistical questions, feel free to email the grad advising team at ceginfo@uw.edu. And if it's related to the field, we can pass it on to faculty. Or if it's related to your application, we can try to help you with that. Any last words?
No, I would just say thanks for joining us, and to follow up on Eric, if you have any question that's really specific to our program, the courses, or research, feel free to reach out to any of the geotech faculty. You can find our emails pretty easily.
Yeah, and if you are around here and you want to talk to us, also stop by. The worst thing that we can say is I am busy right now, but we are pretty open, and anytime that somebody wants to know a little bit more about us, it's a good thing to stop by and say, hey, I am around. We have 5 minutes to talk about the program, and I can introduce you to other students, or we can introduce you to other students and talk to you.
Okay, well, yeah, thanks again, and have a good week to everyone.
Thank you.
Thank you.